Hey everybody, it's Ripley again. We're in chapter 4 now. We're going to do a little probability. Now you may say, Ripley, why are we doing probability? Probability is the engine that drives statistics. It underlies all of the statistical concepts that we deal with when we do statistics. So we're going to spend a couple chapters just kind of putzing around with probability, hopefully taking your understanding of it to a higher level. This textbook may use different definitions, they may use different terminology, but I'm relatively certain that all of you have seen the basics of probability. So I'm going to blow through some of the basics pretty quickly. Hopefully we're going to have fun with a little bit of an applet here in this first section and just get you up to speed if you've not seen it. If you haven't seen it, you come up to me in class, slow me down, keep note cards, keep flashcards, things like that, just to make sure that you're up to speed if you haven't seen this before. Excuse me, I'm going to take a drink. All right, so most people think probability, if I mention the word probability, it's things like let's flip a coin, let's roll a die, let's draw a card out of a shuffled deck of cards, etc., etc. That's a great way to think about it. Keep it simple. Probability can get out of hand. For those of you that have, excuse me, taken like the AMCs or the AIMEs, the probability problems in those are ungodly, but we're going to keep it relatively simple throughout this class. Remember, this is an introduction to statistics, so we're not going to get too crazy. If you enjoy this and you really want to get into it, take a class called Probabilistic Models or Combinatorics. If you can take a combinatorics class, I think you'd enjoy that as well if you like this stuff. I enjoy it. It's tricky as heck. Sometimes I just have to sit back on a problem and just go, oh my God, what am I really trying to figure out here? So if you feel like you're in the woods, you're not alone, all right? And feel free to ask questions and we can play with it. Okay, let's get the basic concepts out of the way. First things first, we're going to talk about what an event is. An event is just an outcome or collection, I'll put this parenthetically, of outcomes. Collections, that should be collection, singular, a collection of outcomes in a probability experiment. And what is a probability experiment, you may ask? It's flipping a coin, rolling a die, drawing a card. Having a child, believe it or not, could be thought of as a probability experiment because it comes out either male or female, although there's some interesting other things that can happen, which we'll discuss down the road. All right? A simple event, as defined by your text, is an event. Okay, Ripley, slow it down. Sorry, guys. It's an event that can't be broken down into simpler terms. It's an event that can't be broken down into simpler events. All right. Then what we've got is a sample space. Again, I'm hoping that you've seen this stuff before. Don't worry about the differentiation between event and simple event, all right? Just think of really what we're going to talk about here is just an event, okay? A sample space is the total set of outcomes in a probability experiment. Probability experiment. Okay? So let's absolutely simplest terms. Let's think flipping a coin. If I flip a coin, the events are either a head or a tail. Let's not even talk about the thing it's landing on its edge, right? That doesn't make any sense, okay? So this is one event. We call that event A, and this will be another event. Let's call that B. That's a sum total of everything that can happen. So the sample space is the set, that's supposed to be set notation, is the set H, T in flipping one coin, okay? Rolling a die, now think about that. If I roll one die, a die. Fun fact, the dots on a die are known as a, wait for it, a pip. all right, or the pips. So let's see, I can roll 1, a 2, a 3, a 4, a 5, or a 6. Let's assume it's a casino die. You're in Reno, so knock it off. This would be event A, B, C, D, E, and F. These are separate events. Now, you could also think of these things. Let's say that I roll a die and I think of an event as rolling an even. Okay, so that event could be written as 2, 4, or 6. That would be the event. Or odd, then the event would be 1, 3, or 5. Now, I should probably write ors in here. This is an or an or like that. The sample space is the set of all possible outcomes in the rolling of one die. So it's 1, 2, 3, 4, 5, and 6. Okay? Now, there are two types of probabilities. There are experimental probabilities, mental prob, and then there's theoretical probabilities. Let's talk about experimental probabilities first. An experimental probability is simply the probability of something happening based on an experiment that you did. So, for example, let's say that you flipped a coin and you did it 20 times, okay? And you got 11 heads and you got 9 tails, okay? The experimental probability of getting a head in this case is 11/20. However, we know that the theoretical probability in this case is, well, it should be 10 out of 20, or 1/2. So the theoretical probability is the probability that we know that an experiment like flipping a head should play out to be. The probability that I flip a tail, or excuse me, that I flip a head on a coin is 1/2. However, if I do an experiment, I probably won't get to exactly 1/2. Think about, for example, rolling a die. Okay? Now, if I want to roll a 6, all right, so I'm going to write this as the probability of rolling a 6. Hopefully we all realize that there are 6 sides to a die, assuming that it's fair and not loaded, etc., etc. There's one way to roll a 6, and there's a total of 6 outcomes that we can have. All right. However, if I roll the die 6 times, I might not get any 6s. So in other words, the experimental probability for that experiment is 0 out of 6. I didn't get any 6s. Okay? So the way that we figure out theoretical probability is very simple. The probability of an event, I could write this as E, I can write it as A, I don't really care. It's the number of ways a thing or an outcome can happen divided by the total number of possible outcomes. Again, it's hard to write down by your belly button and not see what you're writing. All right, this is the theoretical probability. Experimental probability is easy. We just do it through observation. We look. Okay. Now, you may be saying, Ripley, wait a sec. How is that possible? How can we say that an experimental probability of an event is 0 if I roll a die 6 times and I don't get any 6s? By the way, rolling a die 6 times is exactly the same thing as rolling 6 die once. And for those of you that have played Yahtzee before, I think that's 5 dice rather than 6. Dice, excuse me, rather than 6. You know that happens all the time. Well, there's something called the law of large numbers. The law of large numbers. And this is super key. This is so key you have no idea in statistics. The law of large numbers, without the law of large numbers, statistics really wouldn't make any sense. And what this really says is that as the number of times we repeat an experiment, in this case rolling a die, an experiment, heads gets bigger, so theoretically heads to infinity, we know that the experimental probability heads towards the theoretical probability. And I have a cool little applet I'm going to show you here. Theoretical prob. It's kind of neat. Okay, watch this. Let's see. I'm going to pop out of here, and I got this applet. So check this out. What this is, watch this. I'm just going to roll it. I'm going to let n equal 1. Now, watch what happened. Basically, what this did is it rolled the die one time, and it rolled a 3. It's just a simulator, okay? So the experimental probability was 0 out of 1, which is 0. All right? Well, you may be saying, well, really, that's only one roll. Okay, now let's roll it 10 times and see what happens. Watch this. Okay, now watch this little graph. It started at 0. Okay, apparently on the second one I got a 6, so I got 1 out of 2, so it popped up to 0.5. And then on the third, the fourth, the fifth, the sixth, etc., etc., etc. Now look at this. So I've got, how many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which means that this was our first one down here. And then these were the following 10. So when it jumps up, that means I rolled another 6. Then it dropped down, I didn't roll a bunch of 6, and then it jumps up again. These are our rolls. Look at them. You can actually follow them. I rolled a 3. That's what corresponds to the 0. Then I rolled a 6. That popped up to 0.5. Then I rolled a 5, a 4, or excuse me, a 5, a 1, and a 4, which means I rolled 1 6 out of 5, right? So that's going to be around 20%. And then I popped another 6. That 6 corresponds to right there. That got it way up there. Now remember, the theoretical probability is 0.1667, which is 1 out of 6. Now watch this. This perfectly illustrates the law of large numbers. I'm going to roll this thing, whoops, I don't want 100, I want 1,000. I'm going to roll this thing 1,000 times and watch this thing get crazy. Check it out. Just watch this. Now it's rolling. Notice over here on the right, these are the rolls that you're actually getting. Now watch what's happening. As n gets bigger and bigger and bigger, watch what this line does. This little curve, this probability, it's going to have jumps, jumps, jumps. Look at this. We're at 500, what? Getting close to 600. We're above 0.1667, and all of a sudden, slowly but surely, look at her climb. Look at her climb. Or actually, not climb. Look at her descend. Getting closer and closer and closer and closer, and pow! 1011. It's 0.1682. The actual theoretical probability is 0.1667. I'm going to do it one more time, and let's see how close we get. All right? I'll just sit back and let you guys enjoy. We get so close to 0.1667 that it's very difficult to tell the difference between the experimental, which is what this thing is doing right now, and the theoretical. Watch her go. Watch her go. Getting close. 0.1716. So look at that. We had this little hump that we had to deal with. But we're zooming in closer and closer. One more time. Don't be bored. I promise. This will pay off. Oh, now look at that. She's popping up a little bit. Be interesting to see what random number generator they create. And we go. Look at this. And I love this. Getting close. Disco. 0.1667, 0.1674. That is the law of large numbers in full effect. Cool. I hope you enjoyed that. That was cool. Okay, let's go ahead and go over some rules of probabilities now that we know how to define a probability. All right? All right, first things first. We know that the probability, let's see, of an impossibility, in other words, the probability that I flip a 3 on a standard head is equal to 0. The probability, excuse me, of a certainty, all right. In other words, say the probability that I flip a head or a tail on a regular old coin is 1. And the probability of any event is always going to be wedged between 0 and 1. All right. Those are the biggies right now. I know the probability of an event, because think about it. If I also remember, the probability of an event is equal to the number of ways the event can occur divided by the number in the sample size. All right? It's also referred to as the sample space. So this guy is always going to be bigger than this guy, always, unless they're equal, which they could be. Okay? Now, real quick, let's talk about the complement of an event. Meant of an event. And we've got a notation for this. And I'm going to use a Venn diagram. This is equal to the complement of E. Venn diagrams are the easiest way to show this. All right? Check this out. Let's say that this is the sample space right here. This is my sample space. Okay, so it's the set of all the possible outcomes. And let's say that E lives over here. All right? The complement of E is everything that isn't E. All right? E complement, bless it, that just doesn't want to write on it, does it? E complement is all this stuff over here. Now, there's a really powerful little rule that we can pull out of that. If I take the probability of an event and I add that to the probability of its complement, what does that absolutely have to be? Well, think about that. The number of ways that the event can happen plus the number of ways that the event can't happen constitute the entire sample space. And if I take the number of elements in the sample space and divide them by the number of elements in the sample space, I always get 1. Okay? Now, that's just a real general introduction to probability. Now, what we're going to do here, I'm going to throw a little something else at you, especially since we're in Reno. You may or may not be from Reno. Pardon me, I'm going to take a drink real quick. But we're going to talk about odds. And the reason we're going to talk about odds is because so many people screw them up. All right? Odds, first things first, not probability. Probability. They're not probability. I cannot tell you how many times I've had somebody say, yeah, the odds of something happening are 50-50. Or the odds of rolling a 6 on a 6-sided die is 1 in 6. Incorrect. The probability of rolling a 6 is 1 in 6. The odds of rolling a 6 is actually 5 to 1 against. You could also see this written as 1 to 5. This is against, and this is in favor. Whoops, favor. Okay? Now, the odds of an event is typically written as a ratio, and it's the number of ways the event can happen as a ratio to the number of ways the event can't happen or the complement of the event can happen. That's why complements are introduced in this textbook. Now, let me explain what that really means. Odds are there for one reason and one reason only, period, for gambling. I don't care where else you hear them. The whole purpose behind odds, because if you think about it, it's just a little tweaking of the definition of probability. The whole purpose for odds, excuse me, is so that casinos know what to pay. Now, I'm going to go up on a little soapbox here, so bear with me for a sec. This won't take much time at all. Let me explain how odds work. In a fair game is defined as a game where if you play the game over and over and over and over again, nobody wins any money. The house doesn't win any money, and the player doesn't win any money. So you may win on some games, on some individual games, and you may lose on some individual games. But if you play a bunch, if you let that law of large numbers go into effect, nobody's going to win any money. It all comes out even. Okay, so let's think of this. Let's roll the die real quick. Let's play a game called Roll a 6. Okay? Now, again, the probability of rolling a 6 is 1/6. I'm going to write this again. The odds of rolling a 6 is the number of ways to roll a 6 is 1. Okay? And the number of ways to roll a not 6 is 5. All right? Notice, The odds, this ratio always adds up to the size of the sample space, as long as the ratio hasn't been simplified. Let's be real clear about that. Now, what this means is, if I am running a fair game, so let's assume that roll of 6 is a fair game. If I bet $1 and I win, the house pays off $5 plus I get my bet back. That's in a fair game. Okay? That's how odds work. Let's say we were in a game where the odds were, let's see, 150 to 1. 150 to 1. That means if I win and I bet $1, then I get $150 plus my $1 bet back. If I bet $2, then I get $300 plus my $2 back. Now, people often think that casinos somehow cheat. That's not true at all. I'm going to dummy this way down. I hope that I'm not patronizing anybody, but think about it this way. What a casino does is it simply doesn't pay true odds. In other words, in my game of roll of 6, clearly a casino doesn't have a game this simple, but pretty close. In the game of roll of 6, if I win, they wouldn't pay me my full $5 back, plus my bet back. They may pay me a total of $4, which really means that they're giving me 1 to 3 odds, because remember, there's my $1 bet. So if they hand me $4 back, that means they gave me $3 plus my $1 bet back. That guarantees that over the course of many, many, many plays, the casino, even when they pay out, they're actually making $2 over true odds. And that's what true odds are. Okay? Those are what are referred to as payout odds. These are payout. Whoops. I'm sorry, I should have pointed to that. These would be payout odds, and these would be true odds. So these are true, and this is what the casino might pay out on. And that's how the casinos make a lot of money, keep their lights on, and employ a bunch of employees. All right, I hope that was helpful. We'll play around a lot more with probabilities. They're a good time. Thanks for paying attention.